The 2015 Polyglot Gathering is brought to you by italki. Become fluent in any language.
Right, hello everyone. My name is Timwi, and I'm going to talk to you a little bit about Unicode, what it is and why we need it. Now, Unicode is a technical thing that is used in computers. Now, halfway through this talk, I'm going to start getting a little bit technical, but up until there, I hope that, I'm going to fill you in on the basics of what you need to know. So if you fall asleep halfway through, I can understand, but please try not to snore. So here we go. Okay, so first of all, I'm going to explain to you what bits and bytes are. So if you already know that, then come back in 5 minutes. No, just kidding. Okay, so a bit is always 0 or 1. A bit is basically a location in your memory or your hard disk or whatever, which can always have only one of these two values, 0 and 1. So your computer memory will look like a jungle of zeros and ones. It's basically, so for example, if you have 8 gigabytes of RAM, that would be 8 billion times 8, which is 64 billion of those. Okay, and so if you just look at the memory like this, obviously you can't really see any shapes or patterns or whatever. But by conventions, we group them into eights, into groups of 8, and such a group of 8 is called a byte. So within a byte, you can have 8 bits. So we by convention, we assign them numbers. So for example, if you have this particular combination of 0 and 1, that would have the number 70. And the smallest number, of course, is all zeros. We call that 0. And the highest number is all ones, and we call that 255. So that means there are 256 possible combinations of bits in a byte. So in 1960, people started thinking, well, we want to be able to represent text, human-readable text, using bits and bytes. So they came up with the American Standard Code for Information Interchange called ASCII. And so the idea is to have certain values associated with letters, A to Z, lowercase letters, A to Z, and of course punctuation marks like exclamation mark, question mark, the space, etc. And here is the original publication of the ASCII standard. You will notice the letters here, lowercase letters, there are some digits, well actually all the digits are. And you will also notice some weird 2 and 3 letter combinations here. Now, what are they? Well, you see, at the time in 1960 when ASCII was invented, computers didn't quite look the way that they do now. They didn't really have a screen and a keyboard like we're used to now. They looked like this, except that this is not really the computer. The computer is actually a huge machine that is off in a separate room all by itself, filling the entire room. And this is called a terminal. This is where the user sits, types in something on that keyboard. Whatever they type is sent to the computer as ASCII codes, and then the computer comes back with the answer, and the answer is printed on that paper. So the computer needed to be able to tell the printer things like, for example, put the carriage back to the starting point. That's called a carriage return. Or move the paper forward. That's called a line feed. So that's what these codes are. They are instructions for this machine to do things other than printing a single character. Now, the ASCII standard only allocated the first 128, but I've already told you there are 256 possible codes in a byte. So obviously there are 128 codes still available. So what do we do with those? Well, so far we only have the letters A to Z. Now you are polyglots, so you know that's way not enough to write all the languages in the world, obviously. So if I wanted to write German, for example, I would need letters with diacritics or the SZ ligature thing. So in 1983, the Digital Equipment Corporation, DEC, came up with the multi-language character set, MCS, which looks like this. As you can see, there are letters with diacritics, as well as some extra symbols, like, for example, the paragraph symbol, the Japanese yen currency, and maybe some fractions, whatever. And these letters were chosen so that you could write most of the languages which, at the time, had computers in wide use, which was basically only Western Europe and Northern America. So not many languages were covered by it. In particular, so for example, this is French, Danish, and Spanish. I don't even need to tell you that, do I? These languages could be written with that. But of course there are other languages, for example, Hungarian and what is this, Czech, I think, and several other languages. So other corporations, apart from the Digital Equipment Corporation, came up with their own standards within those countries or regions. So those the second half, the second set of 128 bytes would be used to encode letters such as, for example, the O with a double acute, or the Esperanto, like for example C with circumflex, or like an I with ogonek, whatever. And then, of course, as computers spread throughout the world, you also started getting Hebrew and Arabic and Cyrillic and Greek. Now, these standards all got separate names: Latin 1, Latin 2, Latin 3, Latin 4, Hebrew, Arabic, whatever. But the problem that soon arose is when a user in, like, let's say, an Arabic-speaking country wanted to send something to, let's say, a German, then obviously the German computer would assume that you're using Latin 1 because that's what you need in order to write German. And so the Arabic letters wouldn't show up properly. So the problem was that a particular sequence of bytes in your of bits in your email, which make up this byte, could mean any of these characters: AE ligature, C acute, C circumflex, or Cyrillic, Greek, zeta, whatever. So any particular sentence that uses special characters would show up in any one of these ways. Now, who of you knows which one's the correct one?
Last one.
The third one, yes, that's right. That's because it's Esperanto, that's right. Now, if you were in Germany, you would have seen the first one, and you would be left with a guessing game as to what that could mean, even if you knew Esperanto. So, in 1991, people came up with the idea of Unicode. We've seen that the problem is that a particular sequence of bits, if a particular sequence of bits can have one of multiple meanings, that causes the problem. So the idea was that any particular code should encode one character only. But of course 256 is not enough to encode Hebrew, Arabic, Cyrillic, and everything together. So instead of 1 byte, let's use 2 bytes, which gives us 16 bits for each character. That was the idea in 1991. So those 3 letters that we have here, the AE ligature, the C acute, and the C circumflex, which used to be the same code, are now 3 different codes. And you will see that the first one has 8 zeros, followed by the same code that it had in Latin 1, whereas the other 2 get a new code assigned, which is where the 8th bit is now 1, so it's a greater number than 256. So at the time, the hope was that 65,536 combinations, which is how many you can get with 16 bits, would certainly suffice to encode everything that you ever want to encode. But actually, they were focused on a different problem, which is that up until this point, lots and lots of people had lots and lots of data on the hard disk or in databases or wherever in the backups, which are encoded in ASCII. And you see, it's just trust me on this, that it's too much work to go through all of it and convert it all to Unicode, especially if some of it is stored away on magnetic tapes or whatever, or in punch cards, whatever they had in the 80s or before the 80s, I don't know. Wait, what was I? Oh, yes, that's right. So the problem is that if you have a database containing some text beginning with a capital P and a lowercase a, let's say, then obviously these would be the first 16 bits in your database. And if you now flip a switch and say from now on our database is in Unicode, then suddenly this would turn into some Chinese character which you don't want. Right? So whatever text you have in your database would turn into an unreadable jungle of Chinese and Japanese, and you get some funny surprises in there, like this is actually the Japanese postal company logo system symbol or something, and you also get this sort of W with a weird hook. I don't know what language uses that. Does anyone know that? Yeah, nor do I. It's not an IPA letter either, so it's probably something really obscure. So the idea to address that problem is called UTF-8, which stands for Unicode Transformation Format. The 8 is because it's 8 bits, which means that most of the, well, actually, no, not most, but anyway, all of the characters that were in ASCII, all of which have a 0 bit at the top, because ASCII used only the first 128 values, would remain the same. So whenever you encounter a byte that has a 0 bit at the top, you know it's ASCII. But then, like for example, the Cyrillic G, let's say, would be encoded like this. Now the way this works is the top bits of the first byte tell you how many bytes there are in this sequence, and then every other byte starts with 1, 0. And all the other bits, the ones that are marked in blue here, are the actual value of the letter, the actual Unicode value. So you put those together into a single value, and that tells you the number, and then you know that's a G. Okay, now, why don't we encode everything like that? So for example, the lowercase a, which has these bits, why don't we just put them together like this? Well, obviously it takes less memory to use 1 byte, but there is another problem, namely that if we were to allow both, then there would now be 2 different ways of encoding the A. So if you now wanted to search your database for, let's say, the name Paul or whatever, you would have to go through all possible combinations that the P and the A and the U and the L could possibly be encoded. So we disallow this to ensure that there is only one way that the A could possibly be in your database. Now, obviously, this particular code has only 5 plus 6, 11 bits of actual payload, that's what that is called. So we need another way of encoding things that require more than 11 bits, because obviously 16 bits is Unicode is 16 bits. So this is how we do it. We have another byte which starts with 3 ones and a 0 to indicate that there are 3 bytes in the sequence, and then we have 16 bits. Okay, let me try and remember what I'm trying to say here. Oh yes, that's right. Why do we have this extra 1 and 0 in the second byte? Well, you see, because if we did this, then we would have 13 bits of payload. So we could make do with 2 bytes in more characters. So some of Chinese might then need only 2 bytes. Now, the reason we don't do this is because the second byte in this 2-byte sequence would also be the character digit 6. Because this is, it starts with a 0, so this code is actually the code for the digit 6. So if you were to search your database for a digit 6, you would find this even though it isn't a digit 6. It's actually a Cyrillic G. So there are actually some Japanese encodings from the past which actually had that problem. So UTF-8 tried to address that, and this is how they did it. So we disallow that. Okay, so the biggest advantage of UTF-8 is that it's compatible with ASCII. So if you have an ASCII text, you can just flip a switch and it's UTF-8. The biggest disadvantage is that characters do not all have the same bit length, which means that if you have a file that is, let's say, exactly 100 bytes length, in ASCII, you knew that's exactly 100 characters. In Unicode, which is 16-bit, you could say that's 50 characters. It's 100 divided by 2. But now with UTF-8, we would have to go through the entire sequence of 100 bytes to count how many characters are in there. And obviously, that takes a computer a bit longer to do. The 16-bit encoding does not have these disadvantages. Or does it? Well, I will come back to this later. But first, let's look at the claim that 65,536 characters is definitely enough to encode everything in the whole world. Well, there are quite a few languages that use the Latin alphabet, and quite a lot of them have come up with all sorts of different diacritics and combinations of diacritics. Any of you who have ever seen written Vietnamese know what I'm talking about. And yet all of them taken together need only 1,056 characters. So we still have over 64,000 left. Greek is not much, because there aren't many languages that use the Greek alphabet. So that's only 384 characters, and that includes archaic characters, such as, for example, the digamma, which is not used anymore. It also includes all the combinations of all the, what's it called, the stuff that is used to write ancient Greek. Exactly. Yes. Now, Cyrillic-based languages, there are quite a lot, but they don't use the diacritics much, so there are only 304 of those. All Arabic-based languages, again, they do have diacritics, like Farsi, for example, but again, 304 characters suffice for that. The Indian writing system, there are quite a few separate writing systems in India, but every single one of these is used to write only one language, and so there aren't many varieties of these letters, so they only add up to 1,280. We still have 62,000 left. This should be enough, right? So let's happily go on. Korean Hangul, well, all of you who know Korean know that it's actually an alphabet, so it only has something like 30 letters or so. But because the Koreans wanted to combine them with Chinese characters, they put them into blocks of syllables. Okay, so every possible syllable in the Korean language forms a block. So Unicode had to encode every single possible combination that could plausibly come up in a Korean word or name, and that is 11,008 of them. But we still have 51,000 left, so let's happily move on to Chinese and Japanese, the so-called Han characters. Now, I've written something down underneath there to say that obviously before Unicode, the Chinese and the Japanese already tried to encode their languages, and they knew right from the start that 8 bits wouldn't be enough, 256 characters wouldn't be enough. So they came up with Big 5, which was used to write traditional Chinese, GBK, which was used to write the simplified Chinese characters, and Shift-JIS is a Japanese encoding which actually had the problem that I mentioned earlier, which UTF-8 solved. Now, obviously there are more than 28,000, but in the first version of Unicode, they encoded all of the characters from those 3 Chinese and Japanese standards, and that was 28,116. At this point, we have only 23,000 left, which means it's already obvious that if you wanted to encode another Chinese, you'd be out of luck. Now, obviously, writing systems aren't the only things. You also have punctuation marks, diacritics, phonetic notation, scientific mathematical symbols, things like integrals, contour integrals, less than, greater than, subset of whatever. Currency symbols, yen, euro, whatever. There are lots of currencies. You wouldn't believe how many there are. So we end up finding that 65,536 actually is not enough. So what do we do? Now, as a little digression, I'm going to zoom in on punctuation here, because people really underestimate how many punctuation marks there are. When you write a sort of comment inside a sentence, you sort of parenthesize it with dashes. Sometimes you use the so-called M dash and sometimes an M dash. Oh, by the way, I'm just going to explain this here, what this means. This is actually a hexadecimal number. This is not 2014, but those of you who don't know what hexadecimal is, don't worry, you don't need to know. It just means this is a Unicode character, and this is a 16-bit value. Okay, so on top of those, obviously, if you're writing a mathematical equation, you want to be able to write the minus sign, and the minus is not always the same size as the end dash in every font, so it has to be a separate character. And on top of that, if you want to write a negative number, which means you put a minus sign in front of a number, you're really supposed to use the figure dash, which is yet another kind of dash. And then, of course, there's a completely normal hyphen, which we use in normal everyday words, such as, for example, lean to. But then again, this is a very short word, so if you have that word appear at the end of a line, you don't really want the to part to word wrap into the next line, because that would look rubbish. So you're really supposed to use the non-breaking hyphen, which is the same as the hyphen, except that it doesn't do word wrapping. Okay, now, as I wrote this here, it occurred to me that there are these double quote characters, which aren't the same in all languages. Those of you who speak German know that the thing that we use for the open quote in English is the same as the close quote in German, and the open quote in German is yet another character. And then, of course, there are other languages like French, which have their own system, so you have these 2 different characters for those. And French also has this idea that you need to put a space in between the word and the quotation mark, and you don't want that to cause the quotation mark alone to word wrap when this appears at the end of a line. So we have a separate no break space, which is different from the space. Now, obviously, I've used the space here, but you will notice that actually right here there is a bigger space than here, because this is actually supposed to separate 2 pieces of information, and for that you're really supposed to use the end space. Okay, so that's the end of the digression. And by the way, this is the normal slash that you would use in normal everyday language, but then there is also the fraction slash and the division slash, depending on whether you want a number to appear like this or like this. But of course, software doesn't quite always catch up with the ideal of an idea, so there are separate Unicode characters for several of these fractions. And by the way, okay, fine. Okay, so coming back to the idea. In 1996, they decided that 65,500 characters is not enough, so we need a new idea. You could just use even more bits per character, like maybe 24 or 32 bits, but we would run into the same problem that we had with ASCII before, because within those 5 years, people have already stored lots and lots of data all over the world and all over the nascent internet in the 16-bit encoding. So something cleverer needed to be done. So they came up with UTF-16. the idea in UTF-16 is, well, we've already got these 16-bit codes. Let's just keep them. And there are a few codes, namely the codes between D800 and DFFF. This is hexadecimal, which is 2048 different codes. They are as yet unused, so they do not mean anything yet, so we can give them a new meaning. So let's use them as special combining codes, and here's how that works. These are called surrogates. We take this range of 2048 codes, and split it into two groups. They're called the low surrogates and the high surrogates. Sorry, the high surrogates and the low surrogates. Okay, so we might have a combination like this, where the first byte starts with 110110 and then 110111, and then together they form a single character, even though it's 32 bits instead of 16. So you take the payload bits, the blue ones, stick them together, add 65,536 to that value, and then you get the value of the character. So this is what the G-clef symbol, which is my favorite character that is greater than 65,536, would look like in UTF-16. And then, so with this idea, we now have 1,112,064 possible codes, and that should definitely suffice, right? Well, linguists seem to agree that it will suffice until we encounter an alien civilization with another Unicode. Okay, so UTF-8 obviously is easily extended, so we can now have these 4-byte codes with enough payload bits to encode the favorite G-clef. Yes, great. I love the G-clef, it's just brilliant. Okay, so UTF-16 now has the same disadvantages as UTF-8. Characters no longer all have the same bit length. So you could use UTF-32, which basically means you use 32 bits for every character, but then people would argue that that requires too much storage space. Now, in the 90s and early 2000s, I might have agreed with them. Back then, it really was a bit extraneous to use that much space for text, but nowadays, I think it wouldn't be much of a problem. However, for reasons of the historical development that I've just described, software has settled on UTF-16, more or less. And I'm going to show you something. Now, this will be a bit geeky, so because I'm going to bring up Chrome here, and there is this developer console that I can bring up in Chrome, and I can type some commands in here. So I can type something in double quotes, like, for example, let's say Unicode, right? And then I can say .length to ask it the length. Now, Unicode obviously has 7 letters, so it will say 7. So this is not surprising. I can also put a letter which is not a Latin letter, because obviously these are ASCII. So just to prove to you that it doesn't use UTF-8, I'm going to type a Cyrillic character, which I do using a shortcut here. Okay, so this is a Cyrillic J. So if I ask that for its length, it will say 1, because it realizes that it's just one character. But now I'm going to put the G-clef. Once again, I'm going to use a shortcut for this. G-clef, like this. Okay, now, it doesn't actually show the G-clef, because it's not in the font. Because, fonts never have my favorite characters in them. But you will agree that this is one character, okay? It's one box with a question mark inside it, and yet it will say that the length is 2. And the reason for that is because it counts the number of 16-bit things in it. So in UTF-16, it is 2 16-bit things. So unfortunately, software has settled on that, so this disadvantage of UTF-16 is here to stay. So, in summary, before we had Unicode, there were several encodings, and computers sometimes didn't know which encoding a text was in, and then sometimes displayed some garbled text, such as the Esperanto that we've seen earlier. So the idea in Unicode was that a single code should have a single meaning, and vice versa. Several scripts can now be used within the same text. I have not mentioned this before. Before we had Unicode, it was not possible to have, for example, Greek and Cyrillic within the same text. So with Unicode, that is now possible. We discovered after 5 years of using Unicode that 65,536 characters aren't enough to encode all the languages in the world, so we needed more encodings. UTF-8 and UTF-16 were invented. So this means that we still need to know which encoding a text is in. But this disadvantage is not as bad as it was with Latin 1, Latin 2, etc. Because if you have a text in Latin 1, let's say, there is no way for the computer to tell whether it's Latin 1 or Latin 2, Latin 3, Latin 4, because they're just too similar. But because UTF-8 has these marker bits at the beginning of each byte, you remember the ones that are marked in red? It is actually very easy for the computer to go through your email and determine whether it is valid UTF-8. And if it is valid UTF-8, then it's extremely likely that it is intended to be UTF-8. So if you have a text in Latin 1, it is very rarely UTF-8 by happenstance. Okay, so characters do not all have the same bit length, which unfortunately is a problem that we'll be stuck with. And I claim that the advantages that Unicode brings us, despite these issues, outweigh the disadvantages. Thank you very much. And by the way, there is, of course, a Unicode character for the smiley. Here's the code. There is also a Unicode character for the frowny. And recently, Unicode has also encoded lots and lots of these symbols that people sometimes use in text messages. This has originated in Japan. It's called emoji. So Unicode is full of these symbols now. Okay, so thank you. Do we have any questions? Yes, please. Yes, please.
Well, thank you very much for the talk. I'm definitely a non-technical person listening, but I wonder if I want to start dabbling into programming or something like that.
Right.
What would you recommend? What resources or what can I do?
Well, for programming in general, or for programming Unicode?
And both.
Okay.
Thank you.
Well, I happen to be a programmer, so I can answer that question. But to be honest, I'm very reluctant to give you a single specific programming language or environment to learn, because lots of people learn in different ways, and lots of programming languages have different ideas and different stuff. But the thing about Unicode is that it has become so universal that almost all programming languages treat it in exactly the same way. Okay, so if you learn how to use Unicode in any one programming language, then almost every other programming language will do it the same.
Okay, thank you very much.
Any other questions? Okay, right, no more questions. Well, thank you very much for your attention.